So array antennas here means that we will add what we have, the antenna elements, several of them together. And it really builds on everything that we've been doing before, but it will be a slightly different concept. And we will add something called an array factor to analyze these type of array antennas. So we will start with quite a lot of motivation for array antennas, and then we will have 3 lectures where we really talk about array antennas. Before I start with that, we are now exactly halfway in this course. So that means that the examination getting closer and closer for you. Of course, in time, it's quite far away until the examination comes. It is in January. I'm not sure about the exact date. You have the date in the schedule for the course. And I will also upload a few old exams to Canvas so you can see what they look like. In general, I can say that all the exercises that you are doing are very similar to the problems in the exam. So if you understand the exercises, you can do the exercises, that's fine. That's the perfect preparation you should have. And many of the problems in the exercises comes from old exams. And the exam consists of 6 problems. You need 50% to pass. That gives you grade 3. If you get 40 points, you can get 10 points per problem, you get grade 4. And if you get 50 points, you get grade 5. So it means basically you have to solve 5 of the problems. But you also get sub-problems. So if you can solve a problem 50%, you basically get 5 points per that problem. And you will get 3 additional points from this electronic quiz. And the important thing is that that's only for the exam in January. So only for this real exam of the course. It's not valid on the retake exams. So of course you should do the quiz because you learn a lot, but it also will help you on the first exam, and that is the exam that you should pass. And on the final lecture, so in additional 7 lectures of this course, I will solve 1 test exam, so you can really see what an exam looks like. So that is what's coming up in January. And now you also started with the first part of the lab to do your patch design and running FECO to do that design. And you have seen that there are question hours where you can talk to the lab supervisors. So the next hour is basically, I think tomorrow, the times are on Canvas, and then there are additional hours later in the week. So you can see there where you can contact them. Okay, so maybe before I start, are there any general questions about the course?
Sorry, Mats.
Yeah.
Will the exams be in Zoom or in the campus?
Yes, that I should have mentioned. So what everything looks like here, it will be online. So we are reducing teaching more and more because there comes more and more restrictions in the society. And this exam here, I really scheduled for being online. If it does open up so the situation gets much better, then I probably will get an option to either do it online or to do it in class. I already got question from some of you that you were going to travel, think about traveling home or something, and that's fine. Then you will be able to write it online. Of course, you have to make sure that you have very good internet connection, because you will run it live, basically in Zoom, when you do the exam at home. So you need to have very stable internet connection. But otherwise, you can be wherever you want. Yeah. An online way to finish the lab. That is a tough one because the first part of the lab, you do simulations, you can do it, but building the patch antenna and measuring the patch antenna, we cannot do online. And as the situation is at the moment, yes, we are going to run those as physical labs at the university. We push it down to 4 people at each time to do it. So we will have fairly small groups with you. But in that way, we are able to do it. And it's a really good learning opportunity for you because you get hands-on experience of actually building these antennas. You build it yourself, you measure it yourself, and so on. And that is not possible to do online, unfortunately. The exam date is finalized. I don't know the date, but it is finalized. Go to this time edit, you will find it. Everything with the schedule you find in the on the computer. Okay, any other question? Then we will start with the course. So I think I showed you this one on the first lecture, and I showed it also at some other lectures. And this is basically what the course covers. So if you remembered it back now, several lectures ago, I was going through this, what we are looking at the course. And where we are right now is that we have looked at a few antenna elements, not that many, but quite a few. So the dipole you are experts on. You have the monopole antenna, so basically half a dipole. We looked at the helix antenna and the patch antenna. Now you are becoming an expert on because you're designing your own patch antenna. We also looked at some different ways to analyze those, not really FEM and FTTD yet. You used metanomometers in the FECO. And we looked at a few different parameters here. So you know these antenna parameters like directivity and gain and so on. And what we will do now is that we will move on to these array antennas. And that will really be the topic for the coming 3 lectures. And array antennas are very important antenna types because in some ways they don't give a smartness or intelligence to the antennas, but they are crucial when the antennas are used in these kind of systems where we require that the system adapts for its environment. And that is something that is coming in many areas nowadays. So it's something that is in MIMO, for example. So this is a massive MIMO antenna here at the department. Now it's a couple of years old, 5 years old. And here you can see a lot of antenna elements. And this in massive MIMO has been one of the really key components in 5G, where the base stations now gets many more antennas, which means that they can control the radiation to its users in some ways. So that is something that is really coming in everywhere, I would say, in 5G. But it's also something that's widely used in radar systems. It has been used in radars for a long time in a slightly different versions. I would say it's basically less cables here. The reason why there are so many cables here is that each antenna is connected to actually 2 cables in this case, because they have 2 polarizations. So you can have 2 signals from each of these antenna elements here. And the antenna elements you see here are patch antennas. So what you are designing yourself, that is what sits inside of that. And in radars, this has been used a lot to basically track different targets. So we will look at these array factors, which is very similar to our directivity or radiation plots, where you can think that you could steer these beams in different directions. So if you have, for example, an airplane somewhere, you can say, let's follow this airplane in some ways. So you don't radiate everywhere, you just radiate where you have the objects. So array factor will be a crucial component to look at. Side lobes is coming in, and the side lobes is these little tiny lobes you can see down here. You can also see them here. These are high side lobe levels, here as low side lobe levels. Beam steering I mentioned, so that is the case where you direct your beam in different directions. How should you send the signals to direct your beam? Pattern synthesis. In some ways, this is a much better pattern than this one. And that means that the side lobes here are lower. So we need to synthesize these patterns so we get the good radiation properties from our arrays. Here we can see 2 other arrays. These are 60 gigahertz arrays. And I have one of them here. I'm pretty sure you cannot see this in the camera, but you can see it's tiny. It's really tiny. That is the same one as you see here. And at these higher frequencies, these millimeter waves, there the antenna elements are so small, so you can basically put arrays into cellular phones and so on. And that is also the proposed ones for 5G, for example. So it really opens up a lot of possibilities there to do different things. This is another 60 gigahertz patch array. So we will talk a lot about array antennas. So this is what we will go through, a little bit introduction to arrays. That's what I'm doing right now. And then we will start here with some topics, and then we will continue with these topics in lecture 2 and 3 about arrays. So if we think what we learned in the course, it's really that we learned different antenna elements. So we learned in some ways that we have, for example, a folded dipole here. We get some current density on these elements, and the current creates the radiation. So we have this acceleration of this charge on it, that is the current that is moving, and that creates a radiated field that goes out. And we have learned how to determine that radiated field, very similar to the Fourier transform of the current density. We have this phase factor that measures the distance to different positions on the antenna. We also learned about the basic properties of this dipole, droop antenna, patch antenna, helix antenna. How do they radiate? So we learned a little bit about the radiation patterns and so on. And now we're going then to switch this and ask the question, what happens if I put several of these antenna elements next to each other? So I don't only have one patch antenna, I have two patch antennas, three patch antennas, I have many patch antennas. And I want to know, how do they radiate? And that is our array antennas. So let's just start by the simple thing. I put two now, Hertzian dipoles. So the absolutely simplest antenna elements, an idealized antenna elements. We cannot build this one, but we can study it. And that is the one that you have analyzed the most, because you can compute its directivity, its far field, and so on. And that you have done for one Hertzian dipole. Now I put two Hertzian dipoles next to each other. So two separated dipoles. And here the distance is lambda over 2. And what that means is that it's the distance that sits, let's see, between these two here. So here you can see the two dipoles, one on top there and one in the bottom. And the distance between those two is this lambda over 2 in this case. And then it changed its pattern in some ways. So what we can see here is that you get some kind of radiation from this. So this is the magnetic field in this case. So what I plotted here is the magnetic field. I also normalized it with the radial distance. And that is because you know that the electromagnetic fields decay as 1 over r. And if I multiply with the distance, I basically get a constant amplitude of them. And that is what you can see when it radiates out here. So you have a strong radiation there, you have a strong radiation there. So it's mainly radiate out from these dipoles, which is the same as if you would have had one Hertzian dipole. But if you recognize something, you can see here that in some ways the angle where this is strong is actually more narrow now when I had two dipoles than if I had one dipole. Maybe you don't remember that, but that is what's happening. But now makes the interesting fact. Let's move to the right one. And in the right one, I increase the distance to 1 lambda. Now I get a different radiated field. And what kind of radiated field do you get here? You can still see that you have a maximum radiation in this direction and this direction. So that is the strongest radiation, really dark red and dark blue colors coming out there. But then you start getting some interesting things here. If you look at this angle and you look at this angle, what happens there? There the field is very weak. So suddenly you get a case here where basically H is equal to 0. It's at least very low. So something is happening here. And then you get some radiation that comes, let's take another one out here in this direction. And there the radiation is weaker. And those are the side lobes. So you get some radiation in that direction, but you get less radiation than you had in the main lobe, which is the one that sits here. And these are the side lobes. And the only thing I did was to change the distance between these two Hertzian dipoles. And this is the basics of now an array. So in some ways we can change the radiation patterns of the Hertzian dipole, and we can get different phenomena in some ways. Let's look at some other of these phenomena. Now I change the phase of them. So I fix the distance again to this lambda over 2, so the first left case. But now I don't have the same phase of the two dipoles. So I changed the phase of one of them 90 degrees. So basically they don't transmit at exactly the same time. And what do you see then? Then you can see these Hertzian, 2 Hertzian dipoles. Now they start radiating in this direction. So now you have a main radiation in a different direction, and you didn't change the, what to say, the geometry of your antenna. You still have 2 small dipoles. You only change the phase of them. So you basically time delay the signals to one of them. And then you got the radiation to go in a different direction. And if you start thinking, this is actually the key concept that we use in all of these arrays. Because by changing the phase of the transmitted signal, I can make it radiate in different directions. So I don't have to mechanically change my antenna. I can just change the signals. And that's, of course, very easy to do. And then by changing these signals, I can get radiations to go in different directions. So I can control the direction of radiation by changing the phase between the elements. The right one, I make an even stronger change of the phase. Now it's 180 degrees. That means that if one transmits a signal that is 1, the other one transmits -1. So they are opposite in phase, +1, -1. And if you look in the center of this one here, you can see that the top one is either red or blue. And if the top one is red, the bottom one is blue. That is 1 and -1. That is the color scheme that comes there. And now look at the radiation in this direction here. Now that one is equal to 0. Now there's no radiation going out in this normal direction. We call it broadside very soon. It removes that radiation. And I only play with the phase. So that is what we can do with all of these arrays. So of course, we're going to learn how we do this, why we do it. How should we control this? Because you don't just want to change the phase and hope for the best. You want to know how much you change the phase to get the specific direction of your radiation. So the basic idea of this, it really goes back to the beginning of the course and what we've been doing now. And that is this understanding of what these radiation patterns comes from, our radiation vector. So if we now start thinking about, we have 2 antenna elements. I can call this antenna element 1, and this is antenna element 2. And let's assume that I now send a signal from these 2 elements, and I send them at the same time. So we focus on the left picture now on this one first. And that means that when I go to time equal to 1, the field has propagated a certain distance here. And that distance is now described by the distance from the center point to this blue circle. That is what I'm doing. And it propagates a distance because the speed of this electromagnetic signal goes with the speed of light. Incredibly fast, but it's a finite speed. So if I let it go a little bit longer, these circles just move out, and they move out, and they move out. And what I get in these cases is that I get what to say, an added phase front of this, where these are parallel in some ways. So I get some kind of addition in the direction of these wavefronts. And that is why in the previous picture, when I have 2 of them and I had the same phase, the radiation went to right and left. If I go to the right picture of this, and then I say that this element here, 1 and 2 again, the element 2 started sending its signal slightly before. So just a little bit time before. It means that that one has propagated a slightly longer distance. So the circle there is larger. And then if I let time go, so now time equal to 2, of course, the circle gets larger, the same increase of size, and they get larger. And now you can see again that you get a wavefront here, a parallel line there, and the direction of propagation, which is orthogonal to that. And now it's shifted. So if I want to propagate in a direction here that moves upwards, I should send these signals slightly before, because they should reach the receiver at the same time. And the distance is slightly longer for the lower one than the upper one. So let's say I have my Rx here. Then this distance and this distance are not the same. And since they should reach that one at the same time, I have to send this one slightly before. And in the for a fixed frequency signal, that means I should change the phase of them. So time and phase are the same thing. And that is how I control my array to radiate in different directions, this beam form. So this is the basic idea, what we can do with an array. And now, of course, we can build different types of array. And then we will analyze these ones. So the one we will actually focus on this course are these so-called linear 1D arrays. And we do that because it's simplest. It gives you all the understanding. And doing that, we can go to like 2D arrays. We will do that in the course, but we will focus on the 1D arrays. And this is now what I call the left one, a 1D array in the X direction. So I have the X direction here, and then I can have elements here, like element 1, 2, 3, 4, 5, 6, 7, and so on. So there I have an array that have the elements on the X-axis. This is now on the Z instead. So here I have different elements along the Z-axis. And that I call then a Z-directed array. So these are one-dimensional arrays. So just elements after elements after elements. Of course, I can do 2D arrays. So here is a 2D array. And then it covers both, like a plane, in this case, the XZ plane. I can do a cylindrical array. So it moves around here. I just put different antenna elements at different positions in space. All of them are arrays, and we can treat them with similar methods. And that is what we're going to do, how we treat these ones. And the use of these arrays are immense. You have classical phased arrays where you only control the direction where I'm going. You can do slightly more signal processing on them. They call sometimes smart arrays. And of course, we have the MIMO, which is one version of this smart antennas, where you actually have this multiple input, multiple outputs. And in those cases, you typically have one cable to this one to this, and one to this, and one to this. And each of these cables can transmit any signal it would like. In a phased array, all of them transmits the same signal, but maybe with different amplitude and different phase. So you only control 2 parameters in some ways to them. In general, you have a fixed version for the amplitude, and then you can control the phase to control the direction of radiation. In MIMO, you can control basically everything. There are, of course, different versions of this where you control more or less. So some of the properties of this is that it can create antennas with a high directivity, so narrow beam width. You can see one case is up to the left here. You can electronically scan these beams. So very rapidly, you can change where the radiation is going. So think a 5G communication system, you can have users at many different positions. Time slot, you can send it in this direction, another time slot, you send it in this direction, and so on. You might have a lot of airplanes. You can follow the different airplanes with different beams in some ways. So this is what we can use this, what to say, arrays to in some ways. And one more thing we can show in these ones is that in the bottom one, the lower one here has n equal to 2. So this is 2 elements. These are space lambda over 2 now. The right one here has 7 elements. And what you can see that the effect is when you increase the number of elements, you typically get a narrow beam width. So this one goes more and more narrow. It's very wide here and it's very narrow here. So you can push your beam width together. And of course, you would like to have a narrow beam to point in a certain direction. And you also get side lobes. So in the first one, you don't really have any side lobes, this one, just for this particular case. When you go here, you can see you have many side lobes. And typically, the more elements you have, the more side lobes you have. But then we'll learn how we can actually remove these side lobes so we can push them down. And that we can do by different tapering of this. So these are things that we can do with these arrays. I think I got a question here on the chat. And it's how does the distance between 2 elements affect the lobe directions? And what's happening is that from each element, you send a signal at a certain time. And what's interesting is how long does it take for that signal to go to your receiver? And that's, of course, proportional to the distance from the element to your receiver. And that will create a different phase. And then we add the signals with different phase. Sometimes we got constructive interference, sometimes we got destructive interference. I think I got another one on chat. What is the better radiation here? I don't know. Depends, of course, what you want to do. If you think that you have an array, like say radar antenna, I will show you a few very soon, then you would like to have different fairly narrow beams that can point in different directions. If you say you have, for example, a MIMO system at a lower frequency on these ones, you want rather wide beams. So that depends on different, different applications. In a MIMO system, you would like to have beams that are, orthogonal to each other. So they see different incoming waves, or they can transmit different fields. I will show you it also later on the lecture on Thursday, some MIMO cases for this. Let's move on with these ones. So some applications. Radar is really the original applications of all arrays. So phased arrays for radars started to be developed basically during the Second World War, and it's been highly dominated by military applications. But there are many other applications which are not military in some ways. So the first one here is some weather radar. So if you think that you are looking at is it raining in Lund or Malmö if you want to go out biking, for example, you typically, or I do at least, you can go to the Danish weather service and they can show you where are all the rain over Skåne. And you can see right now it's raining between Malmö and Lund, which means I don't go biking home, for example. And you can have that with an array antenna. You don't have to have an array to do that, but that's a typical radar application. So in radar, you determine the distance to an object and typically the direction to the object, which means you can place where it is. And you do that by measuring that you send a signal, how long time does it take for the signal to get back to you? And if you know in what direction you radiated, then you know where that object is. You can then track objects with this, for example, airplanes where they are flying, you can track them. Radar have a lot of applications, sometimes with different name in imaging. So you can do different things of looking at Earth, for example. You can look into the human body and you can try to image what's happening inside of it. Weather, I mentioned. Touchless interactions start to come, or there are speculations in cellular phones that there will come radars inside of them. So you basically don't have to touch your phone. You can still communicate with it. And of course, in military, there are many types of applications. Down here, there is some photo from some missile warning systems, and you can see the size of it by looking at the truck that sits there. So there are many different types of applications for this. And yes, in radar, I will just mention for you, there is a separate course, actually starting just after Christmas, which goes into this radar and remote sensing. So what is the basics of a radar? How can you use a radar? And what is, in some ways, what can you do with it? For example, a satellite radar here can look down on Earth, and you can see, for example, plants. You can see how it's growing and so on Earth from these systems. Other type of arrays, basically all airplanes have array type of antennas, or radar antennas at least. In many cases, there are, in modern ones, there was arrays. Older ones, there were not arrays inside of them. So this is one array antenna. You can see a photo here. And basically every element that you see here is one antenna element. The edge ones of those are dummy elements. They are not connected to anything, but what's inside of them is connected to something. So you can start to see that usually there are quite a lot of elements in these type of systems. This is a broadband version here. So this one here is from 4 to 12 gigahertz. So quite a lot of bandwidth that comes in. And in some applications, they should be adapted also for RCS, which stands for radar cross-section, which means that these antennas should be not so visible for another person or another country if it's a military application. That's a radar type of antenna. Radio channel sounding. For example, at this department, there is a lot of propagation research. So how does radio waves propagate? How does the communication channel look like? And to know that, you can go out and measure it. And to measure that, you would like to measure it with large arrays. So this is one cylindrical array here. You can see the antenna elements that sits there. If you look at them, they are all patch antennas. And they are dual polarized patch antennas. So if you think what you are building right now is an antenna which is typically single polarization, but putting two connectors to it, you can have two polarizations at once. And you can see from the back side here the connectors to each patch. There are two cables that can come into it. There, of course, the one I circled now had no cables, but this one has cables. And you can see there's a lot of cables to this. So this is a patch antenna. Compared to your patch antenna here, you can see it's rather thick, and the thickness of this one is increasing the bandwidth. So you can get higher bandwidth out of this system than you have from your system. And by doing this, you can then measure what's happening when I want to, for example, communicate from here to somewhere else. Does the wave now go and get reflected in the walls? Do they go out through the window? So what is the direction where they actually enter to my antenna or where they leave my antenna? And that comes into something usually called the double directional channel measurements, where you don't only want to measure the time delay and the amplitude of the signals, you also want to see what direction they actually propagate. And that you want to know for a lot of different communication systems. Radio astronomy is another application of arrays, and it's coming huge applications of this of arrays. So I showed you this one before. You can see the size of it compared with the person here. You can see it's huge. And this is actually an array. So here you can see a lot of different antenna elements. That's it. So they're really like separated out. And these are putting here on a rail actually, so they can be moved over this Y-shaped pattern. And what's below this one is Washington, DC. So it's a huge array, that's it. Huge antenna, huge array. It's only 27 elements. So number of elements are not that big. But of course, then they cover here this 21 kilometer long arms in some ways. And what's happening with this kind of system is that you can get an incredible resolution. So you have, for example, here a 3 centimeter wavelength, so 10 gigahertz. You have a resolution of this system, which is 1 micro radians. So 10 to the power of -6 radians. So you can say, I'm looking in this direction. You're not looking in that direction. Extremely accurate where you're looking out. And that's, of course, because the stars are so far away, and you won't have resolution of looking at these stars far, far away, or different galaxies and so on. And the reflectors are also really big in these cases. So the spacing in these antennas are enormous. So if you, for example, had two of these arrays, which are elements 1 kilometer away from each other, it's more than 10,000 wavelengths between them. So this is not something that's called half a wavelength antenna. This is an enormous distance between them. And I will show you why that is useful in this case. So that's also a case where you use arrays.
Can I ask you a question?
Absolutely.
If you go back a slide, what's the Y arms photo like on the bottom left?
Yeah, this one.
Yeah, what does that indicate?
Yeah, so that is where all of these elements can be. So we could think about that. You could have now, you have 27 of these. So it means that you can have 9 on each of these ones. That way you can put your parabolic reflectors. So these are the one that you can see here in this photo. You see all of those reflector antennas, and they are standing on a rail. So basically like a train. And they can move on this rail, which is the one that we have here. So the rail is going here. And that means that you can do a measurement of this by having one separation of them. First one, second one, third one, fourth one, fifth one, and so on. And then you have stretched it out all the way. Then maybe you want to measure a new time and you only want to use this part of it. You want to put them closer together. So you can change your array. Of course, extremely slowly because these are so heavy. And then you can look out at your star again and you will see a slightly different picture out of it.
Thank you a lot.
So you can rebuild your array of these huge mechanical objects. So that is what this picture is showing in this case. So it's an array antenna, very different from your communication type of systems. The square kilometer array is one of the latest versions of these huge arrays, and that is one of the big joint scientific projects in some ways. I know you probably know about CERN, who do particle physics and so on. There are similar ones who are doing astronomy. And the square kilometer array is one of those enormous constructions. So these are still an artist impression here. It's a system that is built on the southern hemisphere, mainly in Africa and Australia, also some few other places. And the idea is to put out a lot of antenna elements. So you can see one version here. This is some type of like dipole type antennas. Here you can see some parabolic reflectors, and you can really see them standing everywhere here. So enormous arrays. And these are not arrays that has to stand now on a fixed distance to each other or a certain shape. This can actually be signal processed. And what you want to do with this is, again, you want to look at the stars. And of course, when you look at the stars, we have to cover that those Earth is rotating. And the positioning of this is actually done so you can cover more due to the rotation of Earth, because you see different pieces and so on. And this is something that's been going on for, I would say, more than 10 years now. The initial construction is coming up now or next year, and it's considered to be operational in a couple of years, like 6-7 years. There's a lot of pictures. If you go to the webpage, you can see it. So these are enormous arrays. And of course, the data this receives is also enormous, and you need to process it. And by doing that, you should get better pictures of the universe in some ways. Typically, you would like to know what is the origin of the universe, the Big Bang, and so on. And that means that, you know, when you see the stars, you look at visible light. That's one tiny part of the electromagnetic spectrum. This one looks at a different part of the same spectrum. And they also see other parts of the electromagnetic waves. Okay, so that is arrays, where we see arrays. Now we're going to, in some ways, analyze our arrays, and we're going to do stuff. So I showed you almost an identical slide to this, I think, on the first or second lecture. When we start looking at how do we get from our current to our radiated field, this radiation vector and radiation pattern. Now we will do the same thing, but we will not talk about a specific current. We will more think here that we have some antenna elements, and the antenna elements are just placed at some position. So if you think about this square kilometer array, it says there is one antenna element, there is another antenna element. Those are the positions DN. And that means that you send signals and you receive signals from these positions. So that's what we're doing. So we just say that the antenna sits at this position, it can transmit or receive signals. And of course, as before, they propagate with a finite speed. And then we have to measure what is the distance to our receiver from this position of the array. And it takes some time. So the distance over the speed of light here. That is how much time it takes. And again, then if you have a time and it takes longer time to some elements, you go to the frequency domain by taking the Fourier transform of this. It means that this time delay comes in as a phase factor. So if you compare the signal in different elements, you have some relative time difference that is coming to these elements. And in frequency domain, it means that I have a phase factor. So I have this multiplication with e raised to minus j omega t. And then, of course, we don't write it in omega and t. I know what my time delay is here. I can plug in my time delay, and I get this e raised to minus j k r. So the wave number k and the distance r. That is what comes in. So the only interesting parameter I have is this distance between my, let's say, observer point, where I want to know what the field is, and the position of my array element. Those are the one I have. And as you recognize, this is basically exactly the same thing as we did for antennas and talking about currents. But now we talk about arrays. But it's the same background to this. So it's a good thing to have as a repetition of you, because this is really the fundamental understanding when you want to understand the radiation patterns. So the same picture again. So since we are interested in this distance, so the distance between our position R and the position of our antenna, dn, I have to calculate that distance. And I now assume that I'm far away from the array. So we are in this far field. So think about this radio astronomy. You have the array on Earth, can be huge, but you're looking at a star incredibly far away. And that means that you can simplify this exactly as we did in the first or second lecture, and we get some average distance, which is this r, and then we get the interesting part, that is the scalar product. And what that means is that I have some fixed position here, r, but my antenna sits there, and I want to compare this distance with this distance. And the difference between those two is the scalar product. So what is the relative distance from the position of my antenna to my center of my coordinate system? That is what comes in. And in all of these cases, yes, I have this phase shift. And that is what's sitting in your radiation vector. It sits in our array factor, exactly the same thing. And when we did this 2 weeks ago, we also got the thinking of this, that if I now move, so I have the center here, I have the next element up there, and I want to look in this direction, what should I do? I should compare the distance there with the distance there. You can all see that the red line is slightly longer than the black line. But now when I make it even longer and longer, they actually approach the same length. And that is what I'm doing, because I'm moving far away from this. And when I move far away from this, the red line and the black line is as long. They approach each other. If I have a changed distance, so instead I have my origin here and I put my next antenna element here, you all see that again, the red curve is shorter than the black. And if I make it longer, yes, it's still shorter. And in this case, there is a fixed distance between them. And that is that phase factor. So it's always how much, what is the change of distance from that antenna position to your receiver point? That is what you want to know. And that is quantified by this projection here. The distance you are looking, so that is the distance here, that is this r hat. And where is my position or my antenna element placed? And I need to compute the scalar product. That is what I want to have. So the cosine between those and the length, dn, that gives it. And that is what sits in all of these formulas. So now we will do this for an array. So what we have learned before is that if we have a current density, a given current density, J of R, it can be on a dipole, it can be on your patch antenna, it could be on any antenna. Then we have learned how to determine the radiation vector from this. So we computed with this formula that looks like the Fourier transform. So think about this as the Fourier transform of your current. Of course, this is over angular parts, r hat, theta and phi and so on, but it's basically the Fourier transform that sits there. Now what I'm saying is that I have the same current on this element as I have on this element. Think about the dipole. But I change the position of it. That's what I do in an array. I shift it somewhere. So what is then the radiation vector from that shifted antenna element? And that means that I have a new current density here, which is the old current density, but shifted some direction d, vector d, that's it. So I need to now determine what is the radiation vector of this JD, because that's my new element. So I want to know what that radiation vector is. And if I plug it in, I should do exactly the same thing with that element. I should take the Fourier transform of it. So then I have this J of R prime minus D. I should take this Fourier transform and multiply with this phase factor. And if I see here, I can now call this one R bis instead. I change a variable in this one. And if I do that change of variable, I just get in some new R prime here. Then I can shift this and move this phase up to the phase term. And the D do not depend on the integration variables. So I can move it outside of the integral. And then the beautiful thing is what's left here, there, and there is exactly the same thing. Because of course, okay, there's still some R bis here, but I can change the variables again. And it's exactly the same thing that's next. So by shifting this antenna element in space, I get the old radiation vector times, in these cases, now here, the important part, this phase term. So that is the added part when we start doing these arrays. We get the multiplication by this phase term. That's all what happens in these cases. So change of space gives, in these cases, a phase shift of the radiation vector. Before we take a break now, do you recognize this from everything, basically? What you've done when you look at time signals, you looked at a lot of like signal processing, time invariant systems. If you time delay your signal in one of them, what happens with the response? You get a multiplication with e raised to basically j omega t, or minus j omega t. It's only this multiplication with this phase term that's it. And that is when you change then your time reference in some ways. Where did you measurement time equal to 0? Where is time 1? You can time delay it. It corresponds in this frequency domain as multiplication with a j omega t, or minus j omega t. And what we do with the antenna is that we change it in space. And when we change it in space, we get exactly the same thing, but we get that factor, which depends on space. And in space, we don't have an angular frequency, we have a wave number k instead. We don't have a time delay, we instead have this factor here, which says what is the time or spatial distance in some ways. And it's slightly more complicated because, of course, in space, you have 3 spatial dimensions. In time, you have 1 time dimension. We have to deal with that there are 3 dimensions in space. And that is the difference that happens in this formulas. And that is actually everything that really happens with an array. And what we will do is then to learn how to utilize this for different things. And that we will continue with after the break. So with that, let's take a break. I will stop the recording.